forgot my whiteboard. Okay. So our first question, what is the importance of symbols and why should we care? Basically, symbols are a shorthand. So like instead of writing the mean of the sample set, the mean of the sample set, the mean of the sample set, every time we refer to it, we can use symbols as a shorthand. And the way that I remember it, we kind of differentiate between and the sample group. And so, let's see. So, sample symbols. Can we see this?
It looks good.
Okay. So symbols from the sample will always be just our regular Latin alphabet. So like the mean, standard deviation, the sample size, and those are actually the most important ones. So the first one, X bar, that is the mean of the sample. S is for the standard deviation of the sample. N is the sample size. The population symbols are usually Greek letters. And so that's the biggest differentiation. So there is a difference between a sample and the population. And so we have to use different symbols, different shorthand. And so typically population symbols will be Greek. So the mean and the standard deviation of a population are the Greek symbols for M and S respectively. Okay. So the first one is the mean of the entire population, and the second one is the hey Bridget, is the standard deviation of the entire population. Okay. So does that answer the question about the importance of symbols? It's basically a shorthand. And it's just a way to quickly refer to these descriptive statistics that we use all the time. Some other letters that we might see, capital E is for the margin of error in a confidence interval. Let's see. This little symbol here, so the P with the little hat, it's actually called P hat. That's going to be the proportion from a sample. But for the most part, the symbols are just used as a shorthand. So you could just refer to the whole thing. You could say the mean of the sample is 25.2 every time in a paper if you wanted to, but it's shorthand typically to use just X bar instead for your sample. And then the population will always be Greek letters for the most part. And that's one way that you can tell the difference. So when you're reading a paper, if they're using Greek letters to refer to their data, it's most likely population data. And if they're using our regular Latin alphabet like this, it's most likely sample data. That's one way to tell the difference between the two.
Brittany, and this is for everybody else. I'm just going to mute everybody else. If you have a question, like either raise your hand or type it in the box. That way we don't get all the feedback. Can you say anything just to clarify, like sample versus population? Like if we're talking about the population, how do we get that? How do we get that information, or is that just like generic?
Yeah, so here, let me draw this little picture. Is the picture coming out backwards or is the picture forward for you guys? Okay, I hope it's right. So cool. The difference between a population and a sample is that a sample lives inside the population, and the sample is always going to be randomly selected. Okay. So that we learned in Ellen's class, right? So there are different ways to select your control group, your treatment group, but the most important thing is that they are randomly selected so that you can make those strong conclusions that we talked about in study design. If you got a group of, say, students, and it's everyone in the class or everyone in the grade or everyone in your district, and those people were not randomly selected, then that's a population. So the biggest difference then is that population will be all or every or the total group. So if you got all of the kids in the class or all of the kids in the grade or all of the kids in these 5 schools, then it's most likely a population that you're looking at. But if you have actually designed it so that you have a random selection, then that's a sample. So with inference, so descriptive statistics can be used on a sample or a population. So we can always find the mean, the standard deviation, so on and so forth. But the inference, which includes the confidence intervals, the hypothesis testing, that would only be done on a sample, not on a population. So if you, say, had a reading intervention that you tried on every second grader in your building, you wouldn't necessarily need to do a hypothesis test because you've done it on every student in the building. Now, if you wanted to draw conclusions about students that you didn't test, then you could. But typically, confidence intervals, hypothesis testing are for samples, and then descriptive statistics can be used for the population or for a sample. We can use either one. So is everybody cool with the difference between descriptive statistics and inference? Okay, so let me clarify that a little bit. So in general, stats breaks into 2 major branches. So on the one side, we have the descriptive branch, and on the other side, we have the inference branch. Okay, so on the descriptive, that is finding the mean, finding the standard deviation, drawing graphs, making tables. Okay, and that's pretty much what we covered in that first weekend of class. So descriptive statistics is your very basic top level, what is this data telling me? And so we find those summary statistics like the 5-number summary, the interquartile range, the quartiles, we draw graphs. That's descriptive statistics. If we want to go a little bit deeper, go beyond the data, that's the inference side. So that's the other side, like this. And on the inference side, we have confidence intervals, we have hypothesis testing, and we haven't talked about it yet, but this next weekend, we're going to get into regression. Linear regression, and that's where we look at data set and try to draw predictions. So the other side of statistics we call inference. And so these are the methods that we were talking about during this second weekend. So that's where we take our sample data and we make statements like with 95% confidence, the true value is between this number and this number. And the reason why we say it like that is because we are building these statements based on the descriptive statistics that we collected, right? So we compute descriptive statistics, and then from that, we can do some inference. So we go from this side to this side when we are trying to draw conclusions. So this side is typically thought of as your starting point. So when you first have data, you start by describing it. You look and see, does it fit the normal curve? Are your assumption of normality satisfied? That kind of thing. And then from here, you can build your confidence intervals, do your hypothesis testing, calculate some regressions to see what sort of further conclusions you can get about the data. Okay, so did Will use these symbols consistently? I think in class, Will stuck to these symbols. I don't think Will used a lot of Greek symbols in class, as I recall. Mostly X bar, S for the standard deviation, N for the size. And again, that's because for the most part, we're working with samples. That the kind of work that we do, we don't typically have population data at our fingertips. We, in education research, will have a sample of students or a sample or a subset or a group. And so I think what Will did is just refer to everything using the sample notation. Population level data might be like, think of the US Census. Okay, that's population level data, where you've got every single or mostly person that could be looked at or studied. So S is always for standard deviation, and X bar is always for the mean. And when you see these symbols, we're typically talking about a sample group. Greek letters are for the entire population. Okay. Of our two sides, the descriptive statistics are pretty straightforward. I think finding the mean and the standard deviation of a data set is not something we'd ever do by hand. Actually, none of this stuff we actually do by hand. And we can get in a little bit to Stata if you want to as well. So because we don't actually calculate them by hand, it's good to understand conceptually what they are. And so it's kind of a flow chart going in this direction. We use our descriptive statistics to build our inference. Okay. And this is why it's really important that you have a good sample, because all of our inference builds on what we started with. If you have a sample that's not representative of your population, if you've got bad data, if you've got missing values, if you've got made up values, your inference will be bad too. So no amount of statistical analysis can save bad data. You can torture it as much as you want to, but statisticians call it garbage in, garbage out. So it's important that we start with good samples. You see this a lot in higher ed. Some of the first arguments around co-requisite remediation was that they only tried it with four-year students. And so when they wanted to implement it in the community colleges, they said there's no way to draw conclusions. So even though the four-year students showed a lot of promise, that particular sample was not representative of the community college students. And so it is absolutely impossible to draw conclusions about data that you don't have. So when designing studies as much as possible, that's why it's important to have random samples so that you can get a good cross-section of your entire population. Because if your sample's not good, nothing good can come of that. There's no way to make up for a bad sampling method. There's no way to make up for a non-representative sample. You can't come back from that. Okay. Alrighty. So this is more of a methods question. And we talked about this a little bit in back in Ellen's class. So you can try to incentivize your survey. You can ensure anonymousness so that people don't feel judged or pressured to answer particular questions, you can make your survey instrument short. Missing values are going to happen, and we can try to minimize those, but there's no hard and fast rule to force everyone to participate in your study unless you have them as a captive audience. Okay, so, okay, I'll read the questions. Yes, absolutely. So the next question, what do you use the T-chart and the other chart for? Absolutely nothing. Take those T-charts, fold them up very nice, and throw them away. They are incredibly outdated. They are a relic from the times when people didn't have access to these wonderful things called handheld computers. And they're just a very antiquated way to compute probabilities. But since we have them, I'll talk about them briefly, and then I'll talk about some better ways. So let me get some room going on my little board. So the two charts that we have from Will's class are actually the result of numerical integration or calculus. So probability is actually based really elegantly on area and curves and calculus, and it's wonderful and it's gorgeous, but I'll spare you all that. The important thing is, though, that there are formulas that can be used to derive probabilities of any type of event. Now, before we had access to computers, those formulas were too complex and they had to be computed numerically, and so people approximated, and that's where the tables come from, back before we had high-powered computers. Nowadays, the tables are a nice conceptual tool to see how probability works. But again, in practice, we use calculators to actually compute probability. So the bottom line is that the charts are for finding probability. That is the ultimate relationship. We use those charts. Uh-oh. I think I froze again, so let me see. I'm going to try to turn my camera off and turn it back on and see if that... Okay. How about now? Am I moving? Can you see me? We're back? Okay, man, we're back. Alrighty. So the charts are for finding probabilities. Okay. So if we ever needed to know the probability that something happened, probability is also synonymous with percentage. So we had a couple of those types of problems in class. So like if we want to know percentage students below that cutoff, that's the probability.
So Brittany, I'm trying to get her out, get her back in. Hope everybody else is doing well. Brittany, you're back?
Yes. Okay. Sorry. I'm not sure what happened. Everything just kind of shut down and stopped working. But you can see me now.
Yep. We're good.
Okay. Okay. So I think what I was saying is that we use the charts to find probability, and probability is used synonymously with percentage. So we can also use the charts for that. So we have two charts. We have the chart for the normal distribution. And that's going to be the chart that we use. Got our little bell-shaped curve here. So we'll use that normal chart if we're wanting to find probabilities for the mean if the sample size is bigger than 30. Okay. We can use the normal distribution, or if our population is normal. Okay, those are the two conditions of using that normal distribution chart. Okay, so if we want to find the probability for a sample, that sample has to be bigger than 30, or we can find the probability for a normally distributed population. Okay. Directly from the normal chart. That chart is called a Z table or a Z chart because it's based on Z scores, right? And you'll remember from class that the Z score formula looks something like that. All right, so if we want to find a probability from the normal distribution chart, we find the Z score. If we're working with a sample, we're actually invoking the central limit theorem. And so the Z score looks like this. You may recall, so there's two Z score formulas. So if we just have a population group, it's the first one. If we want to find the probability for a sample, we're invoking the central limit theorem, which I've called CLT, and the Z-score for the central limit theorem is the second formula down here. So it's very similar. It looks the same. We still take the X value, we subtract the mean, divide by the standard deviation, but we're going to divide by the square root of the sample size. And that's because a sample is going to have less variation than the population. And so the way that we adjust the variation in the sample is to divide by the square root there. Okay, so that's the first chart, and we can do an example or two if you like. Okay, so the normal distribution chart is used when you got a normal bell-shaped, like so, population, or if you've got a sample and as long as it's over 30, the normal distribution will work. Okay, so that's when all is right in the world. The other chart is for the cases where we don't necessarily have so small samples. And that's the T chart. So it's the T distribution, students' T distribution. A fun fact, Tuesday, the 15th was William Gossett's birthday. And as we know, he worked at a beer factory, and Tuesday is celebrated as Stats and Beer Day to commemorate his birthday and the contributions that he made for his beloved beer factory. I was going to post on Facebook, but I was too hammered. Anywho, so we've got a question from Bridget. Do we use that second formula when it's less than 30 people or every time there's a sample? This second formula is for when there's more than 30 people. Okay. So this is for n greater than 30. When there's less than 30, we're going to use the other chart. And yes, the S is the same. It's the standard deviation. So the S in both of these formulas represents the standard deviation. Okay. And these two formulas that I have here for Z scores are for when we have a normal population or a sample greater than 30. Now, the T distribution is called the small samples distribution over here on this side. Okay. So we use the T distribution if we've got a sample less than 30. Okay, so that second chart that has T up at the top is used for small samples. Okay, the charts work the same though, except for with the T distribution, we have to concern ourselves with what are called degrees of freedom. And without getting into too much detail, the degrees of freedom for an equation is how many free variables you have. So how many variables can you change the value of and determine the absolute solution? Again, that's way more than we need to know. For us, the degrees of freedom is n-1, our sample -1. And that's that small sample correction. You'll remember that Will mentioned in class. So in the event that we have less than 30 people, we can use that T distribution to find probabilities. The nice thing about the T distribution is that asymptotically, or as n goes to infinity, it looks a lot like the normal distribution. And yes, so these charts don't matter. They are outdated. But again, they're good for a conceptual understanding. They're good to see how probability increases and decreases if you change the degrees of freedom. And it's good to see how changing the probability in the tail makes a difference. So I don't want to completely undermine our professor, but let's undermine him a little bit. So if you were ever in a policy situation and someone asked you what percentage of your students scored below an 1810 or whatever on the SAT, and if you pulled out that little piece of paper, you'd probably be fired on the spot, because it's not a very precise way. You'll notice on the chart that it only goes out to 2 decimal places. We can get a lot better precision than that using a computer. So the charts are a good place to start, but we typically use some sort of calculator for that. So what is the best online calculator? There's not a best one. And I would say that since we're learning Stata, it's probably smart to let Stata do our computation of those statistics. Most of the examples that we've done in class, and what will happen is that you'll have a data set that you'll probably open using Stata, and then you can just use the built-in functions in Stata to compute your T and Z statistics. But outside of that, what I do is I just search for Z statistic calculator, or I search for T-test. Unfortunately, there's not a standard in the online calculators. Just kind of whatever floats to the top of your Google page is going to be a good bet. If you have a TI 8384 calculator lying around, those are also really good. And that's what I used to teach in my class. You can use your 8384 graphing calculator. It's got built-in functions to do t-tests. Yes, throwback. Those things never die and they never get old. The TI 8384 calculator has the unique distinction of costing the same today as it did 30 years ago when it first came out. They have an absolute monopoly on the market, and they can charge whatever they want to because they have the blessing of AP, IB, and every other standardized test possible. The TI 83 calculator is here to stay forever. So I can show you on the on the TI calculator, but really whatever stats calculator bubbles to the top of your search engine is going to be good. Wolfram Alpha, thanks, Doug. So Wolfram Alpha is a great knowledge engine. If you give Wolfram Alpha a list of numbers, it can calculate all the descriptive statistics. The drawback of Wolfram Alpha is that you have to be able to type in your data. So more than, say, 10 values, and it gets to be a little bit tedious. I don't think, to my knowledge, Wolfram Alpha doesn't have an upload option. So if you're working from a data set with more than 10 or 20 values, Wolfram's not going to be very helpful. So I would say in that case, it's time to just fire up Stata to get your T statistics. Somebody try Siri. I'm not an iPhone user, so I do know that Google, if you type in again a handful of numbers, 5 to 10 numbers, and say find the z-score for this value, I think it will. But for the most part, there's not a standard online for those calculators. It became so easy to program statistics calculators that everybody did it, and that's how we have so many results. I want to back up a little bit. Camille asked when we would use the first z-score formula. Okay, so over here, so ignoring the chart part, it is important to know these formulas. Okay, so being a little cheeky, but the formulas are important for z-scores. There is a lot that we can glean about a data value from knowing its z-score. So there are two formulas here. This first z-score formula, this is our basic vanilla z-score formula, and this is what we're going to use if we know that our population is normal. Okay. So all of our examples from class, we just use this basic z-score formula because we were told at the beginning of the example that it was a normal distribution. So if you have reason to believe that you're working directly from a normal distribution, then you can use that first formula. If you don't, though, so the second one, though, is for samples that are bigger than 30, and actually it doesn't matter what the distribution is. So if you've got a sample that's got some weird skewed shape to it, as long as your sample size is over 30, it's normal. The sampling distribution for the means is normal. And this is what's really amazing about the central limit theorem. It says that eventually everything becomes a normal curve if you try hard enough. So if your sample is large enough, you can use the normal distribution. And the way that you use the normal distribution is with this second formula. Okay. If you've got a sample under 30, that kicks you over to this side. Samples under 30, you use the T chart and the T distribution. Okay. So small samples, we cannot guarantee that they're normal, but the T distribution looks a lot like the normal distribution. The T distribution is also symmetric and bell-shaped. The only difference between the T distribution and the normal distribution is that the T distribution depends on the degrees of freedom. Okay, so the T distribution actually changes shape based on how many data values are in your sample. And the more data values in your sample that you have, so the more degrees of freedom in a T distribution, the more it looks like the normal distribution. And that's why we use the T distribution for small samples. And it turns out 30 is the magic number. Once you've got over 30 and you're looking for probabilities, you can invoke the central limit theorem, and that's this down here. So this is for greater than 30. Okay. Oops. Let me add this back on here. Okay. So finding the probabilities, again, it's an important skill. Being able to compute the z-scores is important. But once you have the z-score, we typically don't go to the chart. We go to an online calculator. I'm going to see, Doug, I'm not sure if this is going to work. I'm going to see if I can share my screen for a sec, and I'll just pick an online calculator. So let's see. Let's see how this goes. Me. Okay. So I hope we're good. So what I'm doing here, I'm just going to type in normal distribution calculator. Okay. And picking the first one that bubbles up to the top is usually fine. If you want some uniformity, in our Brightspace page, Will has linked to a handful of online calculators. And so I won't say those are completely vetted by him, but if you want to use the same calculator every time, in our Brightspace page under content and then links, you'll see that Will has linked out to a handful of these online calculators. So what they all have in common is that they will ask you for the mean, for the standard deviation, and for the z-score, okay? What's really nice about online calculators is that you're not restricted to do that weird thing where we had to subtract from 50 and add up and so on and so forth, because that table that we have can only be used for finding area to the right of the mean, okay? Which is useful if you've got positive z-scores. If you don't, on the other hand, or if you wanted to find a left-hand probability, then that table becomes very convoluted. Another reason why I say just burn the tables. Use it as kindling, keep you warm at night. That's what it's good for. So what we have here, and this calculator, so we can type in a value for our mean and our standard deviation, maybe of 500. And then this one here in particular, it lets us select whether we want to know above, below, and in between. So what's the difference? So if you wanted to know what percent of students scored above a 1300 on this particular assessment, you can type in 1300, and down here we have the probability. Okay, so what's shaded here, so these are all the students who scored above a 1300 on this particular assessment, where the mean is 1100, the standard deviation is 500. Okay. If we wanted to know, what percent of students scored below, say, 900, okay, we can do that, and it updates. Whoops. There we go, below 900. And we've got, oh, I happen to pick a number that gave us a very similar probability down here. And then we can also find in between. So, what percent of students scored between, say, 12 and 14 on this particular assessment. Okay, and so it updates, and we've got this down here. Remember that probability and percentage are interchangeable. They're used interchangeably. And so what this tells us is 14.65% of students scored between 12 and 1400 on this particular assessment. Okay. If we were doing this with the table, we would need to find the z-score for both of these values. We would need to figure out how far they were from the mean, and we'd have to find out what's left over. And you remember the process from class. I actually I don't teach it, and so I'm not sure the exact steps. I kind of just wave my hands and it works. But this is what I absolutely recommend if you ever need to know a percentage or a probability from the normal distribution, is to just grab the first normal distribution calculator that you can find. Okay. And that's that. And this one also will tell us outside. So, you know, what percent of students scored outside to values that we put in, and we can find that probability. Okay. So what students are outside the specific range, and about 85% of students scored outside are 1200 to 1400. Okay, so what this calculator is doing for us in real time, it's computing the z-scores for both of our values, and then it's finding the probability or the area represents the group that we're interested in. I find this just so much easier and quicker than using the tables. So this also works for T. You can do the same thing for the T distribution. So remember, the big difference between the normal and the T distribution is that you need to know the degrees of freedom, and that's always going to be n-1. Okay, so whatever your particular sample size is, -1, and that's your degrees of freedom. So say we have a sample of 25 students, so our degrees of freedom would be 24. Let's see. And so we can fill in, I don't have an example ready for us, but this is all information that we would have. So we would know our sample standard deviation, our sample mean, and you'll notice the notation here. So sample mean is always X bar, little X with a bar on top. And we can fill in these values, and then this calculator will fill in the missing value. Okay, so I don't know, maybe we had a standard deviation of 500 and a sample mean of, I think it's the same. Uh-oh. I'll use the same values that I had from before, and this will find the probability, the cumulative probability, which is interchangeable with percentage. So this could also be read as 50%, say. Okay. So I definitely recommend using an online calculator for finding probabilities. And I'll switch back over to, well, I'll try to switch back over to video here. Okay. All right. And so the biggest difference between them, the normal distribution is used when you know your population is normal, or when you've got a sample that's big enough The t-distribution is used for smaller samples. So when your sample size is less than 30, we use the t-distribution. Okay, sorry. So let me come back here and get a couple questions. So is there an easy way to tell which situation require which estimators or tools? Absolutely. And here's so there was a question, what's the degrees of freedom on the whiteboard? So for the t-distribution, if we're finding probabilities, we use n-1. Okay. Now, there are other situations where the degrees of freedom is different, and so I don't think we'll get into it today. But if we're finding probabilities for a sample mean, which is what we have here, the degrees of freedom is n-1, where n is our sample size. Okay. Now, is there an easy way to tell which situations require which estimators or tools? So in this class so far, we've only been talking about the mean as our statistic. So the mean of, you know, the mean score, the mean whatever. And so when deciding whether to use your Z, which is the normal, or the T, the general rule is it more than 30 or is it less than 30? Okay. Now, I think where this question is headed is the question between, say, a confidence interval and a hypothesis test. And how do you know when to do a confidence interval, when to do a hypothesis test, and what do those two methods tell you about your data, and what conclusions can you draw? And so I think that would be a good place for us to pick up in a follow-up conversation. But I will say that confidence intervals and hypothesis tests go hand in hand. And typically, if you're doing one, you're doing the other. In research papers, you'll see researchers report both, because nowadays it's so easy to get p-values and margins of error. We just go ahead and do them both. So the confidence interval, I don't want to erase my whiteboard, but a confidence interval gives us a range of values where we think the population value might be. Okay, I'm gonna have to break down and erase some stuff on the whiteboard. Okay, so confidence intervals, the way that I explain them to my students, imagine that you're playing darts, but you're blindfolded, okay? So a confidence interval is us trying to hit the bullseye, and all we know is that there is a bullseye and that we have darts in our hand. That's what a confidence interval does. And so the bullseye is the population value. So in a confidence interval, we're not sure what the true value is, but we know it exists and it's there in the middle. Finding a confidence interval is like us throwing darts, right? So we toss a couple of darts at this little board. The level of confidence kind of corresponds to our aim, okay? So you can think of it like that. So knowing how, remember, the level of confidence is not about our sample, it's about the method, okay? So maybe you hit 95% of your shots, okay? That's your level of confidence. So that means about 95% of the time, you'll hit the bullseye or what have you, okay? That's what the confidence level corresponds to, okay? And so changing the confidence changes our shot too. So let's say you don't have a lot of aim. So maybe your confidence is 90%. Okay. That means that the darts that you're throwing are a little bit smaller. Okay. So dots instead of X's. So the lower your confidence level, the smaller your darts that you're throwing at the board. If you have a huge confidence level, say 99%, that's like throwing big, huge. So if you had a dart that was half the size of the board, you could be 99% sure that you hit the target, right? The downside of being 99% sure is, look how big that dart is. You don't have to be very accurate to hit the bullseye with a 99% dart. And this is this trade-off between accuracy and precision. So the higher your confidence, the less accurate your guess is going to be. So for example, we're 99% sure that the average score is between 0 and 100. Well, yeah, okay. But that's not very helpful in terms of analysis. Versus being 90% sure that it's between, say, 72 and 77. So that's a much smaller interval, okay? But you've got less confidence in it. So confidence intervals is all about trying to hit the bullseye with your sample data, okay? And you can adjust your confidence level, but the confidence level only has to do with your aim. It has nothing to do with your data. And that's why Will says things like in repeated samples, like me throwing this dart, we can expect that this would be successful 95% of the time. Hypothesis tests are a little bit different. So instead of trying to estimate the population value, a hypothesis test gives us a level of risk or a level of significance based on our sample data, and that's the p-value. So in a hypothesis test, we're looking to see how likely it is that our data occurred by chance, or what is the risk associated with accepting the null hypothesis, as it were, which we can go a little bit deeper into the weeds. So what I'm thinking is that we need to have a follow-up discussion, and I can talk a little bit more about the difference between confidence intervals and hypothesis testing. Although if you feel like they're very similar, your intuition is correct. They are both methods of inference on the mean. It's just they tell us a little something. They tell us different angles of the data. So the confidence interval, we're using the data to get a range of values. Hypothesis test, we're using the data to get a level of risk. Okay, so they're both based on our sample data. They're both based on a probability. Okay, just a little bit different information, but kind of the same big picture. So we wouldn't necessarily choose one over the other. We would typically do both and use them in a blended analysis. I know that someone else asked, what's the best way to talk about statistics? And so I think that's a good part for a follow-up conversation as well. How can we start to pull all this together into something readable and not too jargony and not too technical sounding? And so I'd be more than happy to let you guys know how I do it and how I talk about statistics in the real world. Outside of just very technical calculations. So yeah, thank you guys so much. I'm glad. I hope you found this useful. I hope you found it informative. I'm gonna let Doug handle the evaluations, but if you've got suggestions for future talks, if there's something else that you'd like to hear, some follow-up questions maybe that we didn't get to, but I think picking up with confidence intervals, hypothesis testing, and how to write statistics would be a good place to start for our next conversation. I don't know when would be a good time. Maybe next week before class. That might be something that we can make happen. I know the homework is due next Thursday too. So if anybody's got homework type questions, we can do that too. But I'm so glad. This is my jam. You guys, I do this day in and day out. This is what I love to do. I teach statistics 5 times a day, every day, 5 days a week. And the story that I always tell my students that I'll also share with you is that when I was in undergrad, I took and I dropped statistics 3 times. And I made it to the same point every semester. They would say random variable, and I would get up and I'd walk out and I'd drop the class. Statistics did not click for me until I got to grad school. The only reason why I have a BS in math instead of a BA in math, because I did go to a liberal arts college, is because I took every math class trying to avoid statistics. And so if I can make it with my extreme avoidance behavior for 4 years of undergrad, you can too. And I'm more than happy to help you get through this class at least. And also then through our capstone project. So just let me know. So thanks so much for joining me. Thank you, Doug, so much for setting this up and making this work. I think this was a great format. So does this record on YouTube? Will people be able to watch?
Yeah, I can post it.
Awesome. Awesome.
We should get some great outro music.
Oh yeah, that'd be awesome. Like we really need to get a podcast
Brittany.
Going. Like I think that would be great.
But you couldn't do the whiteboard, so.
Oh, well, yeah, I guess you got to pick one or the other. Alrighty. Anyway, thanks so much, guys. Thanks for joining us, and I guess we will get a follow-up conversation scheduled. Enjoy the rest of your evening. I'll see you guys soon next week for Stats Part 3.